Hello everyone, this is Yang Kunyu, comes from CTK Library of Mathematical Engineering and Advanced Computing. I'm so honored to be with you to communicate academic questions and ideas. The title of my presentation is a Honeywords Generation method based on deep learning and rule-based password attack. My presentation can be divided into 5 parts. First is the introduction. Passwords are used as a key to access control in every corner of the internet servers. But passwords are and will be an Achilles heel in cybersecurity for the foreseeable future. At present, a large amount of password data has been leaked, and password leak incidents continues to occur. Honeywords is a simple and efficient method that can help the authentication server to detect password leaks. The current research on the Honeywords generation method can be divided into legacy UI-based methods and modified UI-based methods. Generally speaking, the legacy UI-based methods are easy to deploy but have low security, while the modified UI-based methods have high security but are difficult to deploy. Judging from existing applications, legacy UI-based method is the mainstream method and is a hot topic of current study. In this paper, we have explored the application of deep learning in Honeywords generation. We combine the deep learning and rule-based password attacks to propose a new Honeywords generation method called JHDR. This method has high security and the efficiency of Honeywords generation can be accessible. Next is the preliminaries. We will briefly introduce how the Honeywords system works and what is a rule-based password attack method. Compared with the traditional authentication system, the Honeywords system adds a honey-check server. The honey-check server is considered to be safe and reliable. It connects to the identity authentication server through an encrypted and trusted channel. Take the login process as an example. A user inputs the username and password. The server checks if the username is existing and the index of password in sweet words. Then the honey checker checks if the index is correct. If true, the user can log in successfully. If not, it means that a password leak may have occurred. The rule-based password attack is a kind of heuristic password attack algorithm. It can simulate the user password generation behavior by designing various transformation rules, such as insertion, deletion, and reordering to transform the strings in the carefully designed password dictionary. These rules are usually expressed in the form of special symbols. For example, in Hashcat, CO1ant means capitalize the first letter and load the rest, and overwrite character and position at 1 with at. Now let's move to the third part of my talk, which is about Honeywords generation method design. The traditional rule-based methods have high efficiency but have problems in security, while the methods based on deep learning have improvements in security, but the efficiency is not high. So we try to combine the two methods to improve the efficiency of Honeywords generation as much as possible while ensuring security. The research by Pasquin et al. Has pointed out that not all the rules are applicable to a certain password. That is, the generated password obtained by transforming the passwords with an inapplicable rules is different from the raw password. So we aim to build a deep learning model to find the appropriate rules for each password, and then use these rules to transform the password and honeywords. This can be taken as a multi-level clarification problem. There are many rules in a rule set. Each rule is a label. Each piece of training data consists of a password and a corresponding vector. The vector is used to indicate whether each rule and password are appropriate. It can be calculated by this equation, where R is a rule, D is a password, X is a password set. When the generated password obtained by transforming the password D using the rule R appears in the password set X, the corresponding elements of the rule R in the vector is marked as 1. Otherwise, it is 0. The structure of the neural network is shown in this figure. First, the embedding layer is used to obtain the embedding representation of the characters, and then two GCN blocks are used to extract features. Finally, the dimensionality of the result is changed through two fully connected layers. GCN is a type of convolutional neural networks, and it can better exploit GPU hardware to accelerate the training process. Observing the training sample, we found that the positive and negative labels in the samples are seriously unbalanced. Specifically, there are far fewer labels marked as 1 than labels marked as 0. This figure shows the relationship between the number of the label marked as 1 in a sample and the number of samples. Although there are more than 13,000 labels for a sample, less than 500 labels are marked as 1 in most samples. Aiming at this problem, fork loss is adopted as a loss function. It can be expressed as this function. During training, the DAM algorithm is used to adjust the model parameters through backpropagation until the value of the loss function no longer decreases. In order to test the security of the proposed method, we use 4 datasets to simulate the real-world Honeywords generation and the attack process of an attacker. The passwords leaked from RockU and TKTK are used as the passwords known to an attacker, and the password in Gmail and Mopu are the targets of an attacker. Assuming that the attacker used the normalized top PW attack method, the attack results on the proposed method are compared with the PCFG-based method and the tweaking tail method. We use the flatness graph to measure the safety in the average case, and the success number graph to measure the safety in the worst case. The attack results on the Gmail and Maopu datasets are shown in these figures. From the flatness graph, we can see that, compared with PCFG-based method and the twinkling tail method, Using GHDR to generate Honeywords, the probability of one attacker that can successfully identify at one time is greatly reduced. From the success number graph, we can see that, compared with PCFG-based method and twinkling tail method, under the maximum allowed number of errors, using GHDR to generate Honeywords, the number of passwords that can be successfully guessed is greatly reduced. We also test the efficiency of using the GHDR method to generate Honeywords, and the results show that although the average time required for the proposed GHDR method to generate Honeywords for an account is much higher than that of the PCFG-based method and the twinktail method, it still only takes about 3.06 milliseconds, compared with the general network delay, usually 10 milliseconds to 50 milliseconds. It is difficult for users to perceive this time, so it can be proved that the proposed GHDR method is foreseeable in practice. In conclusion, the research content of this paper is an interesting attempt to use a deep learning method for Honeywords generation, but some problems in the efficiency of the proposed method are still worthy of further exploration. That's all. Thank you very much.